with the advent of the idea that magnetic fields created an electric field due to a current, so because if you have a current flowing through a wire, that are charge moving through the wire, there must be a force, which is there means there must be an electric field. There was a guy called Maxwell. His last name was Maxwell, James Maxwell, actually, and he thought that maybe there is a more of a relationship between the idea of electric fields and magnetic fields. It was like, well, if a changing magnetic field creates an electric field, i.e. a current moving through a wire, some charge moving, then there must be some other, he wondered if there was the reverse relationship. And in fact, there is. And this is the idea of an electromagnetic wave. Now, an electromagnetic wave is a transverse wave that involves a changing magnetic field and a changing electric field. It is the creation of the motion, or you could say the motion, or the magnitude that these two change, that really they induce each other to kind of produce and propagate outward. That's the big thing, is it's this propagation of these fields. Now, what happens when is that you get a signal, you get this, an electron or something will emit this when it actually accelerates. And this is when you have a jump from a higher energy state down to a lower energy state or something within an atom, and this emits out this electromagnetic wave. And it depends on that jump whether it emits it in the band of visible light or band of something else. We'll talk about that later on. But this is just the idea. It's a transverse wave. It doesn't need a medium to travel through, and it's a changing electric field which is inducing a changing magnetic field, and a changing magnetic field is inducing a changing electric field, etc., etc., etc. So the electromagnetic spectrum is how we organize these different types of electromagnetic waves. So we've gone through as scientists and physicists, and I'm not saying me personally, this has all been done way a long time ago, and we've gone through and they've been organized and based on their levels of energy, and actually a bit more about the uses that we have for them too. So we go from radio waves to microwaves, infrared light, which is heat, which we've already talked about, visible, which we see, ultraviolet, X-rays, and then gamma rays. Now, we rank them starting with the longest wavelength, radio waves, all up to the smallest wavelength. And this is actually inversely proportional to the energy. So energy is related more to frequency for an electromagnetic wave, so how frequently the wave oscillates back and forth. And it starts with radio waves are the highest energy, the lowest energy, and gamma rays, all the way at the end, are the highest energy, so they have the highest frequency. And as we increase, going up like that. So this is the electromagnetic spectrum. So here's another way of looking at this electromagnetic spectrum. We have the different categories divided out and organized within this chart here, and we correspond them to different frequencies and different wavelengths. So radio waves have the lowest frequency and the longest wavelength. They also have a low energy. And then we move from there. So radio waves also incorporate microwaves within that too. And then we have infrared, visible light, ultraviolet light, X-rays, and gamma rays moving upward in frequency and energy and decreasing in wavelength. When you move upward in frequency, that just means that these waves themselves are oscillating back and forth at that many times per second. So 10 to the 21st times per second is very, very high. And that just, frequency corresponds with the energy. So here's just another way of looking at this electromagnetic spectrum. Speed of light is 3 times 10 to the 8th meters per second. Not the exact value, but as you can see here, it's very close. It's given as a c. We write speed of light c. And it's constant throughout, no matter what. It doesn't accelerate or decrease. Now, this is part of the basis along Einstein's theory of relativity, and was done by two scientists who did a really famous experiment with Michelson and Morley in researching. They were looking at how the speed of light changed, whether you were moving on the Earth, whether you were spinning towards the sun or spinning away from the sun. So what part of the equator you were on, the reason would vary the speed of light. And they did some very fine calculations, and basically you measure it at dawn at one place and you measure it at dusk on the other side of the Earth, and they actually found that the speed of light was constant. So speed of light is constant now. It does travel at different speeds through different materials, but this is the speed of light through a vacuum. So, that we're going to use within our class. 3 times 10 to the 8 meters per second.